Hello friends, welcome to this video summarizing the Computer Binary Circuits course, overview and playlist. Finally, we have come to the end of this course. The objective of this video is to provide an overview, summarizing the course and to produce the list and table of contents of this 5-week course on computer binary circuits. The course is organized in 5 weeks and contains 22 videos. Each video is a lesson explaining how computers perform binary arithmetic operations. The present video constitutes the table of contents of the course and lists the title of each video, the YouTube address where you can access the video, and the duration in minutes of each video. A special effort has been made to keep the videos short, concise, clear, easy to follow, and illustrated with examples. Our scope has been to explain and discuss the features and concepts pertaining to computer binary arithmetic operations, processes and circuits. The know-how of the basic circuits design and implementation, and the successive improvements to make them faster and more effective according to the modern computer requirements. Each lesson is illustrated with examples to facilitate learning and practical understanding of the explanations. This is the playlist of week 1. In this first week, we have started learning the basic concepts of 1's complement and 2's complement, which is a conversion strategy very useful for handling negative numbers and that is used all along the course. Then we continue with the circuits design for the addition of binary numbers, named the half adder, the full adder, and the ripple carry adder. Also, at the end of this week, we introduce the first improvement in addition circuits, the carry look-ahead adder. This is the playlist of week 2. During this week 2, the videos are dedicated to the successive improvements on the addition binary circuits. These improvements are focused in increasing their speed and to make their hardware simpler and more effective. These continuous efforts in computer design is what have conducted the computers to the fast responses achieved today. We learn how to calculate the actual delay of a circuit and how the carries are propagated and generated within the system. With this in mind, we presented 3 successive improvements in the design of addition binary circuits: the carry skip adder, the carry select adder, and the carry save adder. This is the playlist of week 3. During this week 3, we moved on to multiplication, introducing a couple of videos dedicated to explain the basis for the multiplication of signed and unsigned numbers. For the signed numbers, we explain the concepts of range of representation and rules for sign extension, because a good understanding of these concepts is important before dipping in the methodology. We explain that the range of representation is not the same if we are using unsigned numbers or signed numbers, because we need to dedicate 1 bit to the sign. Also, we learn that any signed number can be sign extended to any number of bits, and that with the sign extension, the value of a number remains the same. In one of the videos, we learn how to perform binary shifts, which means how to move in a computer the bits of a number forward or backwards, always maintaining their consecutive order. For this purpose, the circuit of a binary shifter has been presented in detail. With all this luggage, we were ready for the next video dedicated to a new method of binary multiplication called the partial sum approach. The advantage of this partial sum approach method is that it uses less hardware, and as a consequence, it is very useful in applications where there are space constraints. This is the playlist of week 4. In the first part of this week 4, we continue expanding our knowledge of the binary multiplication with 2 videos. The first one dedicated to introduce the Booth's algorithm, and the second one to explain its implementation into the binary multiplication. The use of this new algorithm can further increase the efficiency of the multiplication process. The Booth algorithm for multiplication is a new method based on the pattern of the multiplier bit sequence. The flow diagram and the circuit block diagram of this new method has been presented, and a practical example has been explained in detail. Then, in the second part of this week 4, we moved on to the division, introducing a couple of videos. The first one is dedicated to explain the basis for the binary division process and to understand how the critical step of checking if the divisor goes or does not go is managed in the computer. And the second video has been dedicated to explain the process of a new method called the restoring binary division, which has been designed as a result of the engineering efforts to simplify the circuit hardware. This is the playlist of week 5. In this last week, we explained the implementation of the restoring division circuit. Remember that at the end of week 4, we already introduced the concepts and process of this new method. Now, for the implementation, we split the explanation in 2 parts, part 1 and part 2. In the first part, we present the flow diagram explaining how to convert the flow diagram into the block diagram and how the registers are managed in the computer. In the second part, we present the final logic layout circuit, in particular how multiplexers are used combined with full adders and why we need more processing units when rows increase. To illustrate all these explanations, detailed examples are included showing how the division operation is performed within the computer and how the cycles of operation are implemented. But the application of restoring method to sign numbers requires from extra logic to handle signs. That is why, due to this inconvenience, a new method called the non-restoring division has been developed. This new method constitutes an improvement because it eliminates the need of a restoring step. To better understand this new feature, an example of the non-restoring division is explained in detail. Also, a detailed comparison of the two methods, restoring and non-restoring, is presented. This comparison shows that the new non-restoring binary division method and associated algorithm is more efficient, so that in practice this improved method becomes more commonly used for sign division. Anyway, as a general idea, we conclude that when programming, to reduce complexity, the use of division circuits should be avoided whenever possible in favor of other solutions. And that's the end of this course. In conclusion, because computers are carrying out calculations, the scope of this course has been focused in the brain of the computer, which is where these operations are made. We have made our best efforts to keep these videos short, concise, clear, easy to follow, and illustrated with examples. Your personal attitude and dedication has been paramount all along the course for enjoying the lessons. Your personal effort and commitment has been fundamental to successfully reaching the end of the course. I warmly congratulate you for this important qualification achievement. Please note that at the end of the course we publish the present video, which provides an overview of the course and constitutes the Computer Binary Circuits course playlist. Thank you. Let me encourage you to continue enhancing your knowledge and expertise. To this objective, I may produce more videos in the future. Please keep online.